Hi, thanks for your interest in the talk. I'm Zander Kelley, and this is a joint work with Raghu Mecca. So the main result of the work is a pseudorandom generator for polynomial threshold functions. So this problem is motivated in complexity by average case lower bounds, and also from an algorithmic point of view by de-randomizing randomized algorithms. And specifically, the result of the work is that we give a PRG that's non-trivial even for polynomial threshold functions with polynomially large degree in the Gaussian setting. So talk more about what that means in 1 second. And then a key tool that we'll highlight in the talk as part of our analysis is sort of a Gaussian analog of random restrictions and how they can be used to simplify polynomial threshold functions. Okay, so let me start just by going over some definitions. To define a polynomial threshold function, you can take a multivariate real polynomial P with n real valued inputs and 1 output, and the degree of that polynomial is bounded by d. And then the polynomial threshold function associated with P is just the sign of P. Now, for a visual example, you could take for the set of everything above some surface defined by some polynomial equation. And then the related PTF is the indicator function of this set. The most well-known type of polynomial threshold function is just a half space, which corresponds to polynomial threshold functions of degree 1. So this is just a degree 1 polynomial inside this sign. Okay, so what is a PRG in the Gaussian setting? The most basic thing it does, it's some just fixed mapping that stretches r bits to n numbers. And more specifically, you have a budget of r random bits, and you want some deterministic map which takes these bits and outputs a distribution over Rn, which is indistinguishable from a standard multivariate Gaussian, at least in the eyes of a low degree polynomial threshold function. So your generator needs to be computationally efficient, and in addition, we're trying to minimize these parameters, the seed length r and the error epsilon. And for a given error epsilon, the ideal sort of seed length for this problem looks like this. In particular, it's linear in d, the degree of the polynomial. So this is what you could hope to obtain kind of ideally. And then also, we'll just take a second to compare this to the more standard notion of a pseudorandom generator in the Boolean setting. And the two definitions are very similar, pretty much the same. The only difference here is the type of output, whether you're outputting a Boolean values or real numbers, and then also the target distribution we're comparing with. Okay, so why do we care about the Gaussian case? The more typical thing to study would be the Boolean case. So a couple of reasons. One, just translating the definition of a PRG into a more geometric language gives you a deterministic algorithm for approximating the so-called Gaussian volume of sub-level sets of polynomials. Just some algorithmic task you might care to do deterministically. Now, also, this point number 2, a well-known frontier problem in circuit complexity is to give any explicit function which is average case hard for degree d PTFs. And we would like to know how to do that even for degree larger than log n. That's where we're stuck. And an explicit PRG in the Boolean setting would at least imply some function in NP that does this. It's average case hard, gives you correlation bounds. And the main point here is that the Gaussian setting, it's not so immediately obvious, but it's actually a special case of the Boolean setting. So you can see that by imagining approximating the Gaussian inputs by some binomial distributions, which you represent as just a sum of some random bits. So in fact, if you had a solution to this problem in the Boolean setting, you could solve it in the Gaussian setting, this problem of designing a PRG for PTFs. So, in particular, the Gaussian setting is a necessary step. It's a special case of this problem. So pretty interesting special case, even if you just care about number 2. And then what we're pointing out here is that yeah, PRG with our parameters in the Boolean setting would be great. It would resolve this bottleneck in circuit complexity. Of course, we are only able to obtain it in the Gaussian setting. Okay, so here are a bunch of previous results. The main point I want to make here is just that the problem of constructing PRGs for PTFs is a well-studied problem in both the Boolean and the Gaussian setting. And that up until very recently, we could only obtain a seed length that was like depending exponentially on the degree. So if you remember, we talked about the ideal seed length would be like linear in the degree. Now, a couple years ago, there's this work by O'Donnell, Servideo, and Tan, which made huge progress on this problem by obtaining seed length only quasi-polynomial in D in the Gaussian setting. Okay, so then finally we can talk about our main theorem. It's just directly improving on this result I just mentioned, where we're getting this seed length down from quasi-polynomial dependence on D to polynomial dependence. And then I'll also say that, yeah, independently and concurrently to our work, O'Donnell, Servideo, and Tan, also joined by Daniel Kane, obtained a similar result, also getting the polynomial dependence on the degree. Okay, so let me give a brief overview of the proof of our result, or at least the steps that you need to see a full proof of the result. Certainly, you need to specify the construction, and we'll talk about that just briefly at the very end, but it's not the focus of the talk. We used this construction that was the same as in these two previous works, and our innovation is, in the analysis and not in giving a different construction. Okay, and then I'll point out that our work, as well as these two earlier works that it builds on, each of them gives some sort of thing that could be described as a Gaussian random restriction lemma. Some sort of statement which says that PTFs simplify under, some Gaussian analog of random restrictions that we'll talk about in a second. And what we do in our work, one part of it is we get some, quantitative improvement on this sort of statement, like just a stronger, quantitatively stronger restriction lemma. And then lastly, our different proof technique that we use for the restriction lemma, which focuses on derivatives, which is different than what was done before, also has some downstream effects which lead to a substantially simpler final analysis of the PRG. That's sort of a byproduct, like a qualitative difference. We get this quantitative improvement, but it also has this interesting different focus on the derivatives. Okay, so yeah, in this talk, mostly I want to highlight just this second point about the restriction lemma. So let me talk about some background for random restrictions if you haven't encountered it before. Sort of an abstract version of what you want to say for a random restriction lemma is that when you have some special class of functions and you randomly fix some fraction of the variables, then you want to argue that as a function of the remaining variables, the function is likely to become much simpler in some way. Okay, so that's what this is saying here. And then the classical example of this is the switching lemma. And in the setting of the switching lemma, what you have is a DNF pictured here of bounded width, which I'll say is analogous to a bound on the degree for PTFs. That's like the analogy going on here. And what we want to do is we fix some fraction of the variables as shown. And then the point here is that just fixing a few variables, well, okay, it's not a few, it's most, but by fixing some of the variables, you get maybe more simplification than you would expect, because certainly these variables are fixed, but also you can see that like entire terms are fixed. So these ands, any of the ands that contains a 1, that entire, sorry, any of these ands that contains a 0, that entire term is going to be fixed to 0. And then also, if you have some term that is all 1s, then the entire function is fixed to a constant, fixed to 1. So I won't say exactly how to quantify the simplification going on here, but you can hopefully see or believe that this process is simplifying this function in some way that's like beyond the obvious. Of course, it's depends on fewer bits, but it's like even simpler than that. So what do we want to do here? We'd like to apply this tool of random restrictions in the Gaussian setting, but of course, in order to do so, we need some, just basic definition that captures this idea in the continuous setting. So we're going to describe an analog of a random restriction in the Gaussian setting. That's where we're headed. But to do that, let me first start with a Boolean setting and describe the changes you would make to get to our continuous analog we're going to talk about. So in the Boolean case, what are we doing? We are fixing a 1 minus lambda fraction of the variables and leave the rest unfixed. And what I want to talk about is like some vague sense, the variance left over in the inputs. So I'm imagining that at the beginning, each variable has unit variance. It can vary between 0 and 1. And then after the restrictions, some of the variables are fixed, some of them are free. And I would like to describe the outcome of the restriction as leaving some lambda fraction of the variance on average among the remaining variables. So more specifically, my point is just that all the fixed variables are fixed, they have 0 variance. And then all the remaining variables are still free to vary completely from 0 to 1. So we'll describe them as having unit variance. And then on average, you're saying that the leftover variance in all the inputs is going to be lambda. Okay. So now get to the Gaussian setting. Similarly, in the Gaussian case, we'll want to describe some process which also leaves a lambda fraction of the variance on average in each coordinate. However, the thing different here is that in the continuous setting, we can actually do this more uniformly just by leaving exactly lambda variance in every coordinate. So that's what's pictured here. Finally, you get to the actual, algebraic description of what what we're saying by what is a random restriction or just a restriction in the Gaussian setting. So it's this thing pictured here. So saying we have our function f, and then the restriction of f at x is just this quantity square root 1 minus lambda x plus square root lambda y. And we think of this quantity as a function in y. Now x is just fixed to a constant, it's a function in y. You can see that, since we've scaled y down, the effect of y has been kind of dampened. There's only a lambda fraction of variance associated with y left in this thing. Okay, so this notion, which kind of was identified in previous works as like the right notion of random restrictions in the Gaussian setting, I'll say it's right not just because it's useful, but also if you remember, we discussed this simulation of Gaussians by some random bits. It's also the right definition in the sense that if you do this simulation and then you do actual random restrictions on this Boolean PTF, then approximately what this corresponds to is this thing we have listed here. This definition in the continuous setting of a random restriction. So, and then another, good sanity check to make is that when you're trying to define some notion of random restriction is that something you want to happen is that if you randomly restrict according to your ideal distribution, and then you also set all the remaining variables according to your ideal distribution, this in total, the distribution that you obtain should be the same as the ideal distribution. So just because of properties of Gaussians, that is the case. If x and y are independent here, then you do get just a standard multivariate Gaussian back. Okay, so finally, what we arrive at here is an informal version of the kind of simplification we're hoping to get by applying a Gaussian random restriction. So yeah, what are we saying? That we have our degree d PTF, and you need to set lambda to be smaller than polynomial in the degree. And then with good probability over a random x sampled according to a Gaussian, then the restricted function f at x is almost constant in some way. Talk about it in just 1 second. So that's the kind of simplification you're getting. It's kind of an extreme sort of simplification that the resulting function is almost a constant. And just comparing this to what was done before, there's a similar type of statement, at least implied by both of these earlier works, Kane 2012 and Lodano, Servideo, and Tan. So in both of those cases, you have to set lambda smaller. So in the first work, you have to set it very small, like exponentially small in the degree, to get a non-trivial outcome. And then it was shown in the more recent work that you could set it to be quasi-polynomially small. And then in our work, we're saying you only need to set it to be polynomially small. Okay, so then here is the same theorem with some of those vague terms spelled out. So we said it happens with good probability. It's quantified here, and then said it's almost constant. So that's also quantified here. So what are we saying by almost constant? We mean that there's some common sign C of x, such that as y varies, it's very unlikely for the sign to flip away from C of x. Okay, so that's what this is saying more specifically. And then, okay, you could ask, right, this has seen 2 improvements since Kane 2012. You could say, what kind of theorem could you hope for here? And actually, what we get here is somewhat close to optimal. I mean, it's like at most polynomially away from being optimal, because you can look at what you get for this kind of statement. If you think of f just being a single monomial like x1 to the d, and then just by looking at that case, you can see that you actually need lambda to be at least smaller than 1 over d for this to be possible. So we get something just slightly worse than that. Okay, so that was the second point. Let's just briefly touch on the remaining 2 bullets in the proof sketch here. So this on the right is the form of the output of the PRG. So this is what the construction looks like. What do I mean? I mean, so what this is doing is we're independently sampling some number 1 over lambda we're independently sampling from some distribution 1 over lambda times independently. And this distribution, what we want it to be so-called k moment matching. This is kind of like a continuous analog of ky's independence. And also similarly to ky's independence, you could imagine that the costs in terms of random bits of each independent copy of yi is O of k log n. So this is ignoring some minor details involving choosing some appropriate discretization and instantiation of this. But okay, so this is the construction. And then I just want to talk for a second, like give the slightest idea of how a restriction lemma could be useful for analyzing this construction. So to see how this could be useful, first consider that a truly random standard Gaussian could be equivalently expressed as the weighted sum of some L independent standard Gaussian. So that's pictured here on the top row, these ZIs. Okay, so this is like the target distribution. And we want to show that as far as f is concerned, this thing looks like our pseudorandom distribution. And then this is just what's pictured here is a hybrid argument. I'll say that it's a small lie to say that it's even using a hybrid argument, because everything ends up being pretty tangled and hard to separate in this final like sandwiching type argument. But at least to motivate how it goes, I would say you can imagine trying to use a hybrid argument where you replace one of these truly random Gaussians with our k moment matching pseudo-random Gaussian at each step. Okay, and then why might a restriction lemma help you? Well, if you just look at the difference between 2 rows here, we want to think about this as a function in Z2 basically, or Y2, both of them. And everything else you can call X. So in the sense that we're going to fix it to something, and then we hope that as a function of the second variable here, it's a simpler function. It's like, easy to show that you have this approximation. Okay, so that's really vague. It turns out that it's hard to untangle some things that end up capturing the hybrid argument without being explicitly a hybrid argument, but that's like a very small glimpse into how you actually use this tool that we talked about today. Okay, so in summary, our main result was a PRG for PTFs in the Gaussian setting, and the seed length is only polynomial in the degree of the PTF. And we obtained the result using an almost tight restriction lemma for Gaussian PTFs, which we talked about here, and then something we didn't really talk about today, but another byproduct of our different approach to obtain this restriction lemma is a simpler analysis of the PRG. Okay, so cool. Yeah, I would say the obvious open question is if you could use any of these ideas to try to do better in the Boolean case. And for example, you could ask if Boolean PTFs simplify under standard Boolean random restrictions in some way. And then another question not pictured here that I think is also interesting is to try to get a restriction lemma which holds with higher probabilities. So the one that we have, it's like getting this really stringent outcome, which is that you're almost fixed to a constant, but maybe you can try to say that the polynomial is almost fixed to a degree d/2 polynomial. I think that that's plausible. You could try this to show that that happens with much higher probability. So that would also be useful for trying to improve maybe the dependence on the error, which is pretty poor in our work and all previous works as well. And then, yeah, more abstractly, you could say, are there more applications of this idea of Gaussian random restrictions and these kind of restricting lemmas? So thanks for your interest.